Good day. The problem is about conduction. A wall of 20 centimeter thickness put up as an insulation in an oven has its thermal conductivity given by K is equals to 0.5 quantity 1 plus 10 raised to negative 3 T, where K is the thermal conductivity at and T is in degrees Celsius in watts per meter squared Kelvin. One side of the slab is exposed to convection at 300 degrees Celsius with H is equals to 40 watts per meter squared Kelvin, and the other side is exposed to air at 30 degrees Celsius with H is equals to 20 watts per meter squared Kelvin. Determine the heat flow through the wall per unit area. So the given is the thickness of the wall, which is 20 centimeters, and the the side of the slab, which is exposed to convection, represented by the hot air, is 300 degrees Celsius to the cold air, which is 30 degrees Celsius. The thermal conductivity of the wall is given by the equation of 0.5 quantity 1 plus 10 raised to negative 3 times T. Since there are no given surface area of the wall, we assume that it is 1 square meters. We are required to determine the heat flow through the wall, represented by Q sub T. We use the general molecular heat transfer equation, which is Q sub X is equals to T sub I minus T sub A all over R sub I is equals to T sub A minus T sub X all over R sub A. This came from this equation came from the basic equation, which is rate rate of a transfer process is equals to the driving force, which is the temperatures, all over the resistance. This is also related to the Fourier's law of heat conduction in fluids or solids, which is Q sub X all over A is equals to negative K dt over dx, where we all know that resistance is equals to delta X all over K times the area. Now, solving for the resistance, we use 1 over HA for the resistance of the cold and the hot air, for it is in heat convection. Substituting the values, we will have 0.025 Kelvin per watts for the resistance of the hot air and 0.05 Kelvin per watts resistance for the cold air. Now, substituting the values for the resistance of the wall, we have 20 centimeters converted to meter is 0.20 meters all over the equation for the thermal conductivity multiplied by the assumed surface area of the wall. Since we don't know the temperature in the wall, we assume the value of it by substi by substituting the assumed value to the equation R sub A and substituting the value of R sub A to the total heat transfer equation, which is the temperature of the hot air minus temperature of the cold air all over the total resistance, which is 0.025, 0.05, and 0.3636. And we came up with a heat transfer of 615.60 watts. To check if the assumed temperature is really correct, we substitute the computed values to the general molecular heat transfer equation. And if the assumed value is not equal to the original values, which is 30 degrees and 300 degrees Celsius, then the assumed value will be considered wrong. We also assume values such as 300 degrees Celsius and 250 degrees Celsius, but none of them is equal or at least approximately equal to the original values. When we assume 248.8 degrees Celsius, we came up with the temperature of 30.026, which is very near or approximately equal to 30 degrees Celsius. But for 300 degrees Celsius, it is very far and the discrepancy is very large. Therefore, it is not it is still not yet considered. And finally, when we assume 283 degrees Celsius, we came up with a very near values of the temperature for both 30 degrees and 300 degrees Celsius, and therefore it is considered to be the right temperature for the wall, and the heat transfer computed using this assumed temperature will be considered to be the required answer for this problem, which is 696.77 watts.